So again here, theorem 4.9 is the second derivative test. It says let f be a function such that f prime of c equals 0, and the second derivative of f exists on an open interval containing c. If your second derivative is positive, then f has a relative minimum at that point. Remember, it has to be a critical value here. It says if your f double prime of c is negative, then it has to be a maximum. So again, if f double prime of x equals 0 at that point, the test fails, and you have to use something else. It might be a max, it might be a min, it might be neither. So in this case, you would have to revert back to the first derivative test. Okay? So how do you do it? Again, step 1 is find the first derivative. Step 2, set that first derivative equal to 0 or undefined. Step 3, find that second derivative. Step 4, plug in the values from the first step, or I guess step 2 now. Plug those values in to the second derivative, and the last step is interpret your answer. If the second derivative is positive, remember second derivative positive would mean it's concave up, so that point has to be a minimum. And if the second derivative is negative, remember the second derivative negative means it's concave down, so that point must be a maximum. Okay? So let's give an example using the second derivative test. Remember, if the problem on the test says using the second derivative test, you must follow this process. So find the relative extrema of f of x equals negative 3x to the fifth plus 5x cubed. So step 1, find the first derivative. So f prime of x, it's a simple polynomial function. The derivative of negative 3x to the fifth would be negative 3 times 5x to the fourth, which would be negative 15x to the fourth, plus the derivative of 5x cubed would be 5 times 3x squared, which is 15x squared. Step 2 in that list that I wrote there is actually find the critical values. So we need to set this equal to 0 or undefined. Well, it's a polynomial function, so it's never undefined, so let's just look at when it's equal to 0. I can factor out a negative 15x squared from both of these terms. If I factor out a negative 15x squared, what would be left in the first term would simply be an x squared. Let's be really, really careful again. 15x squared divided by negative 15x squared would actually be a minus 1. So when I do this, I set each term equal to 0. Minus 15x squared equals to 0. Divide both sides by negative 15, I'd have x squared equals 0. Square root both sides would give me x equals 0. X squared minus 1 equals 0 is the other factor. Add 1 to both sides would give me x squared equals 1. Take the square root, remember positive and negative, would give me x equals negative 1 and 1. So these are my critical values. Those are when the first derivative is equal to 0 or undefined. So rather than determining my intervals and testing points in each intervals now I'm going to move on to the second derivative. So let's find that second derivative. The second derivative would be the derivative of negative 15x to the fourth, which would be negative 15 times 4x cubed. So that would be negative 60x cubed. The derivative of 15x squared would be 15 times 2x, would be plus 30x. Again, I do not set this equal to 0. I do not set this to undefined. I don't do any of that. What I do is I take the critical values from the first part and I plug it into the second derivative. So let's go to step 4. Let me move this out. Here's step 4. Step 4 is I'm going to take x values and I'm going to plug them into the second derivative. Again, the second derivative is negative 60x cubed plus 30x. The numbers that I have to plug in are negative 0, and 1. Negative 1, 0, and 1. So let's see what happens when I do that. Again, all I care about is the sign of these numbers. So negative 1 cubed is negative times a negative would be a positive 60, and then we would have minus 30, so that's going to be a positive number. Because my second derivative is positive, I know it's concave up, which tells me that point is a minimum. Look at 0. Negative 60 times 0 cubed plus 30 times 0. That's 0. That tells me the second derivative test doesn't work. So what I would need to do at that point in time is use the first derivative test. Let's try plugging in 1. When I plug in 1, it would be negative 60 plus 30, which again is a negative number. A negative number means I'm concave down, and if I'm concave down, that tells me that that point is a maximum. Okay, so let's look now at what step 5 would be. Step 5 would be determining which points are actual maximums and minimums, and the way that you do that is you actually have to plug it into the original function. Remember, the original function here is negative 3x to the 5th plus 5x cubed. Negative 3x to the 5th plus 5x cubed. The numbers that we know for sure that we have to plug in are negative 1 and the numbers 1. So let's try plugging in the. So when I plug a negative 1 into the function, I'm getting a value of negative 2. Try the same thing again with your calculator, plug in the number 1, and I'm getting a value of 2. Again, because my second derivative was positive, meaning it's concave up, that tells me that the point negative 1, negative 2 has to be a minimum. And at 1, the second derivative was negative, which means it's concave down, tells me that point must be a maximum. So the point 1, 2 is a maximum. So from the second derivative test, I know that there's a maximum at the point 1, 2, and I know that there's a minimum at the point negative 1, negative 2. So the only thing left to do is to look at the point 0, 0. And this is a real cruddy example because at the point 0, 0, how do we determine whether it's a max or a min? We actually have to go back and use the first derivative test. Well, if we're using the first derivative test for the point 0, 0, we might as well have used it for all of the dang points, right? But that's what we have to do. So I'm going to go on to step 6 here, which is not really part of it, is check first derivative test. Check the first derivative test on both sides of 0. So remember, my first derivative, the critical values I had were negative 1, 0, and 1. So what I need to do is find some point in between each of those points. So how about an x value of, I don't know, negative 0.5 and an x value of 0.5. And now I'm plugging this into the first derivative, f prime of x, and the first derivative in its factored form was negative 15 x squared times x squared minus 1. So if I plugged in a negative 1/2, my first term would be negative, my second term would be negative as well, which would tell me my first derivative is positive just before it. If I plugged in 0.5, I'd have 0.5 squared times negative 15 would be negative, 0.5 squared minus 1 would be negative, and a negative times a negative is positive. So again, my first derivative goes from positive to positive, so that means at x equals 0, it's neither a max or a min. So, really stinks because we ended up having to do the first derivative test anyways, but you can see the second derivative in action for the values of x equals negative 1 and the values of x equals 1. So again, for that second derivative test, you have to find the derivative, find its critical values, find the second derivative, plug the critical values into the second derivative. Positive means it's concave up, which tells you it's a min. Negative means it's concave down, which tells you a max. Plug it into the original function to get the ordered pairs, to get the points on the graph, to know whether they're actual maxes or mins.